A very good morning to everybody. It's my great honor and pleasure to have been invited here to deliver this talk. I thank Professor Sinha and Professor Dixit for giving me this opportunity. So I'll be giving you a brief overview of the research that we've been undertaking in our group for the last several years. So we've been working on machine learning for long and deep learning thereafter. So to give you a brief introduction, when you have machine learning, the traditional kind of learning, you have to have a domain expert to extract handcrafted features, and then you feed it to a decision making system. However, in deep learning, you have huge amounts of data as is available today in multimodal forms, and then the system on its own extracts the features and arrives at a decision. So shallow and deep learning, as I've said, so machine learning traditional is shallow learning. You don't have so much data, you have a domain expert to extract the features, whereas it is otherwise in deep learning. So the key advantage of deep learning is in automatically learning good features. So why in medicine? Because there's a lot of imperfection, imperfect knowledge, there's incomplete understanding of the biological mechanisms, imprecise test measurements, uncertainty of the ranges of the results, simultaneous presence of more conditions, more than one condition, missing information. Therefore, you have the scope of learning, some kind of intelligent processing and automated analysis, and now it is as assistive intelligence and not as a self-sufficient system, because we don't intend to replace the physician or the surgeon, but to assist them given the huge volume of data, because it is the human end user who is responsible for any medical decision. And also you need interactive or active learning, because there is insufficient annotation, and thereby there needs to be a continuous feedback between the medical professional and the system. Then there is a genomic issue to that. Of course, we'll be hearing about that in one of the subsequent talks. So it is found that there's a domain called personalized medicine, which needs to offer the right drug to the right disease at the right time with the right dosage. So given a set of patients and a certain drug prescribed, depending on the genetic composition of the individual, you can have 4 different situations. And we are obviously interested in the situation where the drug is neither toxic but is beneficial. So the genomic component also has a major role to play. Today in the hospitals, you've got robotic surgery. Recently in Eastern India, Manipal hospitals projected this, and so you have Da Vinci, the robot. Then India made SSI Mantra, which is India's first indigenous surgical robotic system at half the cost. And the advantage is that since there is precision in the measurements, you use the medical imaging, and the surgeon looks at the machine, whatever the robot is seeing, and operates the robotic arms to get a high precision surgery, which results in a faster recovery and loss of fewer working days of the active person. The patient can get back to life, a normal life. So this is what is segmentation. When you have a, let's say this is a brain scan, so there is a tumor there, brain tumor, the inner part. And when the system can give you an automated delineation of the different regions, it can act as an assistance to the surgeon, who can then take the decision and operate. So in our team, we have been working on these aspects like automated severity level grading of lung diseases, automated grading of prostate cancer, early screening for diabetic retinopathy, then segmentation with resource efficient models, because resource efficient means lightweight models such that the carbon footprint is less, because of course you have the computational expenses involved, and we don't want to make it bad for the environment, as good as possible. Because each GPU consumes a lot of computational resources. So then disease classification in multimodal framework and computer aided diagnosis with imbalanced data. Why imbalanced data? Because in medical images, in disease images. Imbalance is a major issue because suppose you have a tumor in a certain slice of the brain, then obviously the tumor constitutes a very small percentage, let's say 0.5% of the voxels, whereas the majority of the region is consumed by the background region. So if you want to have a decision, and if you are unable to pinpoint in that small tumor area, even then your model will give you 99.5% accuracy, which is meaningless. So you need to focus on the low volume, or let's say those 0.5% of actual region which is of interest, the disease region. You want to operate that. So this is called imbalance learning. So you need to develop certain loss functions, algorithms to handle that. So this is another important problem. Histopathology, first let's go to histopathology. This is of course you know that in cancer diagnosis this is the biopsy is the gold standard even today. So you have to look at the scanned tissue slides, and the pathologist looks at it and makes a decision. And since there is huge volume of data, automated processing has a great possibility. Now that is not a simple problem, which we'll see just now, because there are different issues involved. So this is a low resolution image of the slide. This is a medium resolution, so this part is expanded here and this part is expanded. This is the high resolution one. Obviously the high resolution image gives you more detail for the doctor to see. But the caveat is that the computational complexity will become much larger, because here the resolution is higher and the number of resources you need is much more. So we need to arrive at an offset, and it is a truth, it is a fact that academia doesn't have that much computational resources compared to industry. So we have to arrive at an offset. So when we did the experiments on this kind of data, we were forced to stick to the medium resolution one. Then the other aspects are like image blurring, then tissue tearing, tissue folding, and staining from a marker. So these are difficult for a computer to analyze. Maybe a human being can handle it better because of the better cognitive capabilities. Then when the tissues are coming from different pathological labs, the stains used can have different shades. And then the same tissue from the different labs can have this kind of variations, which obviously becomes very difficult for a machine to analyze. With that, let's move on to the first application that I start to explain here. So the whole slide image of prostate biopsy, of course, this was taken from the publicly available PANDA challenge on Kaggle. And what is normally done is a Gleason pattern score is provided, and today you have the ISUP grade, and the transformation from the Gleason to the ISUP grade is according to this table. And what happens is the majority, the highest grade obtained in Gleason score and the second highest grade obtained in the Gleason score, they are summed together by this tabulation. And ISUP grading is supposed to be standard one today in prostate cancer grading. So what we did was, so the whole slide image you see is so large, a CNN or a standard deep model cannot handle such a huge volume at the input. So we had to resize. Now resizing destroys details. So we extracted some small patches from each of the slides and discarded the patches that were mostly white. Now the problem that remained was, for the whole slide we had the grade because it was annotated. We didn't have the individual grades of the patches. Okay, so this was the model that was used. Of course, we used the EfficientNet B1 model because it was lighter, lightweight, we needed less resources. So this was the whole slide. We partitioned it into bag of patches, and we had a hierarchical framework of the EfficientNet, because it was observed that the grades 0, 1, 2 were more clustered together, had more confusion within them, and the grades 3, 4, 5 were more clustered, because obviously 3, 4, 5 were the higher grades and 0 is the normal, no cancer, and 1, 2 is the lower grade. So anyway, this is the structure. The next one was on COVID-19, also on, this was done quite a few years back during the COVID times. We were sitting at home, and this is the publicly available data. You remember it first came to China and not much data was available in the public domain. So this was how a lung looked like in those times. And so at that time there was not much annotated data available. So we had the training data which had only 2 classes because annotation was insufficient, and the testing data had 4 classes. So this is the beauty of the problem, because you are training on the data set A, the sources are listed here, and the testing was made on the superset of the training set in that sense. So we propose the domain extension transfer learning, where the domain D is represented by the tuple where this domain is the domain DS is a subset of the target domain. So the objective of transfer learning here was to learn the target conditional probability distribution in DT with the knowledge gained from DS by solving TS such that DS was a subset of DT. So in the model form, the CNN was trained from scratch on the 2-class problem. The final layer had 2 nodes, and then we replaced the last fully connected layer of the pre-trained CNN with 4 nodes, because the target domain had 4 classes, and the rest of the weights were frozen, and only the final layer was trained, and the evaluation was on the data set B, which is a superset of the training set. We use 3 conventional well-known models, AlexNet, VGGNet and ResNet, with this domain extension transfer learning, and the confusion matrix showed that it worked pretty well on the test data. This was a visualization generated with the GradCam. Next, we move to the diabetic retinopathy problem, which we handled thereafter. This was a project we had actually under DBT with Shankara Netralaya and Mohan's Diabetics in Chennai. So this is these basic slides are borrowed from my medical collaborators. So diabetic retinopathy, you know that India is the diabetes capital of the world, and diabetic retinopathy is a disease which silently affects the eye of a huge number of individuals, particularly in the village areas, because you know the ladies don't go to the doctors often, and they think it is cataract or eyesight myopia, and when they realize what has happened, by that time it is irreversibly gone and it's causing blindness. So this is the non-proliferative or the preliminary stage, the different stages, and then this is the proliferative or the severe stage, where it is a point of no return. The objective is to catch them, screen them, so that you get it at as early a stage as possible. And the tragedy is that 90% of the vision loss due to diabetic retinopathy is preventable if it is detected early and treated timely. With that in mind, you need to screen them regularly. And the problem is that we have 22,000 ophthalmologists in India, but over 74 million people with diabetes, particularly in the villages, to be screened annually. And in diabetes, what happens is there are different kinds of pathologies which develop in the retina, and these are microaneurysm, hemorrhage, soft exudate, hard exudates. And the doctor grades the diabetic retinopathy by, if you divide the eye into 4 quadrants, so how many of the quadrants are affected and to what density they are affected, that determines the grade. In this project, up to now, we have been able to generate, now Indian database creation is a very important problem. As you know, in the publicly available domains, you have mostly the Caucasian data, and even if Asian, it's the Chinese data. Getting Indian data is very difficult, and we know that the genomic wise we are different, and training on the other kind of data and testing on Indian data becomes a major issue. So one of the major problems is generating Indian data. So here we generated a large-scale, richly annotated multimodal diabetic retinopathy database, SANMOD, from Shankara Nethralaya and Mohan's Diabetics, and this was the data set reported, and thereafter we benchmarked it, and this has been recently published. So it provides 4,200 high resolution fundus images, and it has the different kinds of pathologies. And after that we have been developing a tool for this. It looks like this. We won't go into the details because I think we'll be short of time. So these are the different kinds of pathologies that stand there. And I'll just skip through these because I don't think we have time. So this is weighted deformable DeepNet. So we introduced, so this is a PhD student who has finished the PhD, and she introduced the deformable convolution. So the deformable convolution is able to handle in a better manner for segmentation. So this is the normal convolution and this is the deformable convolution. So we are able to model in a better manner. This is the architecture and the comparison with state-of-the-art models. This is how over the iterations the modeling becomes improved when you have this deformable convolution. This is the parameter-wise contribution that ours was computationally competitive compared to some of the others. And finally, the hybrid models. This was also the contribution of one of my recent PhD scholars who is present here today. So you see what, so the convolution network have a complexity order of n, vision transformer have order of n square, the state space and XLSTM have order of n. So here we have 4 kinds of hybrid models: the wave coformer, UVix, LSTM, ROT-UVL, and EcoMamba all pursue global understanding at linear cost. So in wave coformer, you have wavelet component to handle the temporal or the spectral features along with the spatial features. This is the structure of the model and some qualitative map of how it improves. It reduces the false positive and the false negative and increases the true positive at a reasonable computational cost. Then the vision XLSTM, to overcome the high computational burden and the high resource demands, we explored the vision XLSTM to capture the global context in a computationally efficient manner. So you have the architecture like here you have the vision XLSTM, the bottleneck. Thereafter so this is the qualitative map. Thereafter we introduced the rotational model, the rotational UVIX LSTM to handle the volumetric aspect from the different angles. So it was modeled like here you had the rotational model so that the volumetric information could be better represented. This is the qualitative map, and finally the state space model, which had the sequential bottleneck had to be removed. So the EcoMamba net with the complexity order of n, and this is the architecture. So you have the module here. This is how the qualitative map looks like, and so now the comparison between these 4 hybrid models based on the number of parameters, the number of T-flops, on the time and the memory. And now when to use which of these 4 hybrid models. So when you need maximum accuracy on edge or mobile devices, we propose ROT-UVIL, UVIX LSTM for real-time applications as in image-guided surgery. It is fastest. And wave coformer for offline analysis as its spectral spatial fusion achieves top-tier overlap accuracy. EcoMamba net for accelerating clinical workflows on limited clinical hardware. And now I won't go into the detail, but the thing is that misuse of AI can happen when you just ask chatbot everything. And then I thank my students, some of my students without whom this journey would not have been possible. Thank you.
So nice talk, ma'am. I just wanted to know from your model of AI, how accurately did you predict the COVID pneumonias? I mean, you had those 4 different divisions.
At that time?
At that time.
Yeah, so at that time the accuracy was good, but you see the limited data set available was not very great at that time, and the more data you have more accuracy, higher accuracy. Deep learning needs more data. At that point of time it was good. But obviously it will be better if it is done on present day data.
So, I am a clinician. First of all, it's surprising that we have a session on AI in medicine with not a single speaker from medicine. People whom we are trying to assist. That's interesting, but let's go away from that. Our understanding on the clinical side, people who have been seeing patients, and there are systematic reviews showing that the performance of AI in diagnosing and helping with diagnosis of COVID-19 was absolutely zero. The problem is, there are multiple problems. The first thing is, if you ask 2 doctors to look at the same thing, they themselves don't agree. So we are actually trying to predict something which is, we don't know what we are trying to predict. Secondly, the biggest problem that I see as a clinician, it's a black box. When you take 1,000 COVID-19 X-rays and 1,000 non-COVID X-rays and you use AI to distinguish and find some features, till I don't know what it is looking at and whether that's a good predictor, I am not going to use this. And that is, I think the basic thing is believability and the liability. And the thing that I'm worried about as an elder physician is that when AI shows me something and when I look at it and I find that there is something odd, I'm able to call it out. My problem is my younger colleagues who are now trying to do this on AI, they look at it and they don't even pick up the difference, and they don't pick out the, we somehow think that everything in medicine is science. Unfortunately, medicine is far. When I see something and there is something unusual in a corner, I raise an alarm and my brain thinks that there is something different. The biggest problem is when AI tells us something, we are not willing to believe it. If I were to do today and it were to tell me that Jupiter is the smallest planet and AI were to tell me, I would believe it. That's where the problem is. Yeah, that's the question.
Sir,
the question is COVID, in our understanding.
Sir, I got part of it. So the thing is, just like you are a senior physician, and you have said that your younger colleagues take it in a different way, handle it in a different way. Similarly, you have been trained on the data or on the techniques by your seniors or by looking at the patients. Similarly, the AI model is learning from the data. It's some kind of human-like learning, and so the more data it is exposed to and the more situations it is exposed to, its learning will improve. Just like you are able to distinguish that certain thing is happening in the corner, similarly a new model may not be able to handle, just like your younger colleagues. So given large volumes of data and of course high computational power, which is why we want to get lighter models, then we can expect that the AI model will become better, and that's why we don't intend to replace a physician but to assist, so such that experts like you are at the end to take the final decision. And today you have interpretable AI. So it is providing some interpretation on why it arrived at a decision for people like you to verify, and whether you wish to accept it or not is on you.
Yes. So that was an excellent talk. My question was about the prostate cancer stratification that you showed. So my real question is an extension of what was being discussed earlier. To arrive at that score, how much or how comprehensively did you have your training data so that you could minimize the number of false positives? So, because over there the real challenge is tumor heterogeneity as well.
So that we had a doctor from the Tata Institute of Cancer Research in Kolkata in that research, but the real problem was getting the real data. We worked on the publicly available data, so that is a disadvantage to that. So given the limitations of the whatever data we were exposed to, we could validate with the doctor involved about the results that were obtained on the unknown data which was available in that set. But of course, I cannot vouch for what will happen when some other unknown data is provided, because then the training needs to be taken. So that was more an academic work, and of course, to make it deployable, it needs more exposure. Exposure is an issue.
I think in the interest of time, we'll have to stop, but let's thank Dr. Mitra again. All the speakers are available over coffee. Thank you very much.